All right. Last time we discussed the method of ZVT, zero value time constants. And we saw that in general, for a transfer constant, for a system with a transfer function, h of s, right, that can be written as in this form, a0 plus a1s plus, etc., a2, etc., and then in the denominator you have a b1s plus all the way to bn. We determined, we proved that basically that b1 is exactly equal to sum of what we call zero value time constants. In other words, if you have n energy storing elements, you look at the time constant associated with each one, zero value time constant, which means that you set all the other independent elements, all the other energy storing elements to 0, which basically means that the capacitors become open circuit and the inductors become short circuits. And then you look at the resistance seen by that reactive element. If that reactive element is a capacitor, that would be RC, that resistance times the capacitor would be the time constant. If that reactive element is an inductor, it would be that inductance divided by that time constant. So we showed that this is the case, this is exact. And also we showed that A1 is in fact the sum of the same zero value time constants times what we call the transfer constants associated with that element, which is basically when the way you calculate it, that you infinite value that, let's say it's a capacitor, you short circuit that specific capacitor, and you open circuit everything else in this case, and you see what that transfer function looks like. So it would be a constant. In other words, h of I is h of s for all c's. So ci going to infinity, and all cj's that are not equal to ci, or let's say all cj when j is not equal to I, are 0. Right? So in other words, if you have a transfer, if you have a system, let's say this bubble with, let's say for now, to make it simple, just let's think about the capacitors, and the same thing applies to inductors. So you have a bunch of capacitors, and then this is your Ci. When you're trying to determine the transfer constant Hi, what you do, you say, I set Ci to infinity. In this case, for a capacitor, it would be a short circuit, and everything else would become open circuit because everything is zero valued. And you look at the ratio of this to that. It's a low frequency calculation because now all the energy storage elements are either short circuited or open circuited. Right? So it becomes a low frequency calculation. And that was the A's. That were the A's. So the other thing that we did last time was that we said, okay, we can estimate in the situation, we said, assuming that you have no dominant zeros, meaning that assuming that h of s, let's say for h of s having this form, so there's no dominant zeros, we said that you can approximate this around omega, so let's say around omega h, to be a first order system, and this is an approximation. And if that were the case, then B1, so an approximation of omega h would be 1 over B1, which would be 1 over the sum of the zero value time constants. This equality, this part is exact. This is the assumption. This is an approximation, right? Now, whether or not this holds depends on a lot of different things. We also saw that B1, we knew from the past that B1 itself, so here, B1, was also the sum of the reciprocals of the pole frequencies. But we saw that there's no, despite the fact that this is also, these two are both exact. So these two sums are the same. There's no one-to-one correspondence because, for example, this could be complex. The number of these and those may not be the same, etc., etc. So these were the things that we did last time. And we did use this to, as a way of approximating. And the major advantage of that is that you can actually write these time constants independently in a circuit. And it's a design tool because it allows you to evaluate these zero value time constants independently and use them to identify where the major source of bandwidth degradation is and use that to enhance it. And we saw a design example, right? We went from a basic common emitter, and then we saw that we were dominated by tau mu in that case because of the Miller effect. Then we said that we went to cascode. We reduced that time constant. Then we were limited by the load capacitance and the load time constant. And then when we added a buffer, a follower stage between the output and the load capacitance to make the resistance seen by that capacitance smaller. And then we saw that we significantly improved our bandwidth when we did that. And that's where we stopped. So that was a case that and the estimates were kind of close. And we saw that it's always conservative. The paper that you have, this paper by Brian Hong, also gives you a more detailed, exact analysis of how conservative this can be. So it gives you the lower and upper bound of this calculation. But anyway, so that was what we did last time. So now this time we are going to look at a few cases where it starts to kind of fail in different ways. And the reason we do that, so it's important to see the regular case, and then we are basically looking at pathological cases, some pathological cases, because that would guide us into and lead us into a more general thinking about how to think about these things. This is an approximation, and approximations are good for design, and we will see that we can make modifications to it to make it better, or if we need to, we can go actually to the more detailed calculations. But it's important to understand where it works, when it works, and when it doesn't. So you don't do more work than you need to, right? Okay, so let's do a couple of examples. We'll do a few examples, and they are designed to be relatively simple, but also informative to give you the essence of what you can expect in different scenarios. So the first example we are going to have. So these are examples of somewhat cases where things start falling apart a little bit, and we'll see why and how. Imagine a follower stage. Let's make it a MOSFET. So this is a common drain or a source follower with a capacitive load. So let's use a current source. There's some I bias here, and then there's a source resistance R1, V in, and V out, right? And there are, let's say there's a capacitive load, CL, and then these are these two capacitors, CGS and CGD, which will show us C pi and C mu to make it simpler, right? So we know what the stage does from a low frequency perspective, right? What is the DC gain of this stage? What's the low frequency gain of the stage, the way it's drawn? Well, it's a resistive divider between Rm and infinity. So it's 1. Right? So the DC gain of this thing is exactly 1. So that's one thing we know about this stage, and that's fine, okay? What else do we know? The other thing that we know is that, and we can make it parametric too, so in a second I will do that. But if you want to know before we do anything, how many poles and how many zeros do we have? Again, let's use the guidelines that we have developed, and we'll arrive at the final complete guideline in a couple of lectures for knowing how many poles and how many zeros. But we know how many poles do we have, right? How many degrees of freedom do we have, right? How many independent initial conditions can we set? 2, right? Because look here, this from an AC perspective, this is ground. So this is a capacitive loop, right? So if I set any two of these two capacitors, set the voltage on any of two of these two capacitors, the third one will be already set, right? Because they are in a loop. This is shorter to here, really, from an AC perspective. So there are 2 degrees of freedom, so there are 2 poles. And how many zeros? Well, we have to see how many non-zero HIs you have, or what's the highest order of HI that you can have that would be non-zero. So what's the largest number of capacitors that you can simultaneously short circuit and get an output, non-zero output?
Just C5.
Just 1, right? So the largest number of capacitors that you can simultaneously short circuit, or the largest number of reactive elements that you can simultaneously infinite value more generally, is 1, because it's only C pi. And if you make C pi infinite value, And is it the left half plane or right half plane 0? Does it change the polarity? It doesn't change the polarity, so it's a left half plane 0. So we have 2 poles and a left half plane 0. Just by looking at it, you can tell. We don't need to go anywhere farther than that. Okay, so now we can actually let's try to apply the method of zero value time constants for bandwidth estimation and see what we get. So what we can do is, let's say, okay, so there are 3 time constants here, right? So you have, and there are 2 poles. So you see there's no one-to-one correspondence. This is another example. So you have a tau pi 0. What is tau pi 0? What is the resistance seen by C pi when all the other elements, reactive elements, are 0 valued? So this is not here, this is not here. And from an AC perspective, this is open. So whatever current you push into here will have to go through Rm. So it's Rm, right? So it becomes C pi Rm. And then what is tau mu 0? What is the resistance seen by C mu? If you null all the independent sources and all the other elements are 0 valued. What resistance do you see looking across here? This is ground. What do you see looking from their side? What is the resistance you see that C mu sees? R1, right? Because it's basically just connected. R1 is grounded on this side. So it's going to be C mu R1. And then what is tau L 0? What is the resistance by CL, seen by CL? What do you see looking into the source? Rm. So it's another Rm. So it's CL Rm. So the time constants are pretty straightforward. So let's put some numerical values on them just to get a sense. So in this case, just let's assume that we have a GM of 20 millisiemens. Let's say C mu is 10 femtofarads. C pi and CL are 50 femtofarads. Let's say those are the cases, and R1 is, let's say, 100 ohms. So if you just take these numbers and plug them into those equations, so what are these time constants? So you got 50 femtofarads times, and Rm, so this would correspond to what Rm? Of 50 ohms, right? 1 over G. 50 ohms. So it's 50 times 50, that's 2.5 picoseconds. This is 10 times 100, so it's 1 picosecond. And then this is, again, the same thing, 2.5 picoseconds. So the sum of the time constants, B1, sum of the time constants, zero value time constants, not all of time constants, is basically 6 picoseconds. And then based on this, the estimated omega h, if we take this approximation, is going to be, which is approximated as 1 over the sum of the time constant, zero value time constant. This is going to be, I think it's going to be, 26.5 gigahertz. So it's 2 pi times 26.5 gigahertz. Okay? So that's what the zero value time constant estimate is. Now, if you look at the simulation results for this, which is you can find on page 161 of your handout. So let's look at that. You can see the amplitude and phase plots. Now, what do you notice in there? Do you notice something interesting or rather interesting? Let's see if it makes sense in terms of what we expected to see. So we said that it should be 2 poles and 0. So when you have 2 poles and a left half plane 0, right, your phase should transition only by 90 degrees. So it should drop, in this case, going from 0 to negative 90 degrees eventually. So the excursion of the phase is correct. The final slope of the amplitude plot, if you look at it, it's also, you can see that you get a negative 20 dB per decade slope, right? So that's correct. But do you see something unusual in that plot? Or a couple of unusual things related to each other. Well, unusual is not necessarily the right word. Different from the previous ones.
The phase undershoots negative.
Yeah, phase undershoots, but also phase transition is pretty fast. Because the phase transition, usually for a regular real pole happens over 2 decades from 0 to 90 degrees, right? It goes from a decade below to a decade, approximately, not exactly, it just goes beyond that. But and this is happening over less than a decade, right? The other thing that you see, if you look at the amplitude plot, look carefully around the point it transitions. You see a little bit of an overshoot. It's not a lot, but you can see it. It's about 1/4 of a dB of overshoot there. So these are telltale signs of something, right? The phase transition is faster, and there's overshoot. Those are signs of complex poles. So you have complex poles in this case. And in fact, if you look at the bandwidth estimate that SPICE gives you, so simulation, so SIMS predicts a bandwidth of 45 gigahertz. So now you can see that it is conservative, all right, but it's probably, maybe if you wanted to use it for estimation of bandwidth, then yeah, you have to realize it can be, in case of a complex poles, it can actually be quite conservative. I mean, it's off by almost a factor of 2, right? So that can happen. But the reason here is the fact that this sum, which is equal to this sum, is completely oblivious to the imaginary part of the poles, right? The imaginary part of the poles, if they have complex conjugate pairs, will disappear in this sum. So, for example, if you have poles that are here, or a pair of poles that are here, would produce exactly the same sum, right? Because the real parts are the same. It's just imaginary. Anyway, so you have to be careful. So if you have something that has significant effect in terms of the complex part of it, then it would not show. So that's one example. And we'll see what happens. So basically what it means is that then you have to really think about B2, the higher order terms. And then we'll talk about B2 and higher BNs and all those things. So that's why one of the reasons we need to think about that. So when we get there, keep this in mind. That is an example. And there are more examples of that too. OK, so that's one example. So now I'm going to give you another example of something. And let's say you make sometimes, for example, when you are trying to create amplifiers, especially if you are to have discrete circuits, you end up with a situation where you have a coupling capacitor. So you have an R1, and it's going to a transistor. And I'm not showing the biasing details here. So this base is somehow biased. There's some current source biasing it or something like that. And I'm not showing those things in this to make it simple. So let's say there's a capacitor here. Let's call it a coupling capacitor. And then let's only consider C pi to make the circuit simple enough so we can actually talk about what we are trying to talk about. So this is V in, V out. This is R2. OK. Now, this circuit, what's the point of CC, by the way? Why would you use that coupling capacitor? Make a high pass, essentially. A lot of times, it's actually used to separate the DC bias of one part of a circuit from another part, which is basically the same thing as saying a high pass. But you want to be able to bias this independently from this side. You don't want if your bias, one side is biased at like 3 volts and the other side is biased at like 1 volt, and you don't want to kind of like match them perfectly and all those things, and you don't care that your gain at DC, then you make this capacitor. Now, let's say if this were an audio amplifier, what do you think this capacitor should be, small or large? Relatively. You want this capacitor to be what at your frequencies of interest? Do you want it transparent, right? You want it to be short. And for a capacitor to be short at frequencies of interest, let's say if it's an audio and you're trying to kind of amplify anything like from 20 hertz and above, you can imagine that this capacitor should be pretty large, right? It's a coupling capacitor. So if I just go, so you can see that in this circuit, and if I ask you how many poles, how many zeros, what would you tell me? How many poles do we have? 2 poles, right? You can set 2 different initial. How many zeros do we have? 1, right? Because if you short circuit this one, you get a non-zero gain. But if you short circuit this one, you've short circuited the input, so you don't get anything at the output. So it has 2 poles and 1 0. We know that. What is its gain at DC, at its very low frequencies? What's the gain of this amp? So if I ask you what is H0, which is A0, the low frequency gain, right? What is it? How do you calculate that? You set all the elements to 0 value, you see what comes out. What is it? 0, right? Because this is going to be open circuit. There's nothing going to go through. Nothing's going to go through that. So it's 0. So you can see that its low DC gain in this case is 0, right? And so what does the transfer function look like for something like, and what is the infinite gain? I mean, gain at infinity, like if I short circuit everything. If I short circuit all capacitors and open circuit all inductors. Infinite value then. 0 again, because now this guy is going to be 0. So I know I have a circuit, so how would the transfer function look like? So if it's log of omega, I know at DC, its gain is 0. At infinity, its gain is 0. But there's some middle, if you pick these values properly, I mean, for any values, but if you pick them properly, what happens is that there's a middle of the range where you have some gain. Right? So it's a band pass response. Now, this high pass part of this, so this is what we call omega L, and this is what we call omega H. Right? This band, the low pass, the lower frequency part of it, the high pass part of this, is caused by what? Is induced by which capacitor primarily? Which one's responsible for it? CC, right? No, this part. Because this is the one that open circuits, right? And then this part is responsible, caused by C pi, or if you have C mu's and other things, they would kind of produce that. I mean, we just ignore those to make this simple. And we said this has 2 poles and a 0. And the left half plane 0. So where is the 0? Where are the 2 poles, first of all? Where are the 2 poles? What frequencies are they at? Omega L and omega H in this case, right? In this case, they happen there. Because this is, you started up going up, just it made it flat and it made it drop. So the 0 must be at negative infinity, or basically at 0 frequency. So there's a 0 at the origin. That makes it go up, and then at omega L you hit it. So now if I use the method of 0 value time constant blindly, if I say, okay, B1, this is always true. I mean, it is the sum of all the 0 value time constants. So what are the 0 value time constants? So I can calculate tau C0. What is the time constant associated with CC? You null the independent source. This is shorted. What do you see to the left? R1. What do you see to the right? R pi. So it's R1. So it's basically CC times R1 plus R pi. Right? And what is the other time constant? If you just go and apply it, right? Tau pi is 0. What is the resistance you see here? R1 parallel R pi, right? So you can see C pi R1 parallel R pi. So you put these things in there, you get some sum, and if CC is large relative to C pi, which typically it should be, this is like, so this is going to be dominating, right? So you get something like that. What do you get? You get this frequency in this example. Now, when we talk about the method of infinite value time constants, we'll see how to calculate, how to estimate the omega L in general. And we'll see that there's a slight variation to it. But it's interesting. It's a kind of dual to this. But we are not talking. In this case, you get the first pole. Approximate that first pole. So you will get something around here. But what if you say, well, I wanted to get this guy. I wanted to get the high pass response. How do you get that? Well, you could say, okay, well, let's go calculate B2. We could do that. But there is a better way to think about it. There's a simpler way to think about it. You remember in the beginning we said that any transfer function could be divided into a high pass and a low pass. These were the inverse poles and inverse zeros responsible for it. There was a mid-range, so we wrote the transfer function as 2 parts, right? So that's the left part. Now, we could also look at only one part. So we said, for example, let me just rewrite that to refresh your memory. So let's say there's this part, which was written as 1 minus Z1 over S, these are inverse zeros, right? Because they're flipped. Z2 over S, all the way to 1 minus Zk over S, and 1 minus P1 over S, 1 minus P2 over S, all the way to 1 minus Pk over S, right? Then you times A mid, the mid-range gain, times now the poles and regular poles and zeros. S over Zk all the way to 1 S over Zm. And then here is 1 minus S over Pk all the way to 1 minus S over Pn. Right? Well, I should have used my color code properly. Okay, let's do it properly. 1 minus S over Zk S over Zm. And let's make this. So what you have here, this stuff is due to that, and this part of the transfer function is due to these, right? You've separated those.
The denominator for the red should all be p's, right?
Yes, this should be, yes, thank you. This should be Pn, thank you. And this is Zk. Okay, so you can see that right? There are two parts. There was this kind of factorization that we formed. But now you can also do it in circuits itself. You can say, you can kind of like be judicious. You can say, okay, which one of these capacitors are the ones that when I am in mid-range, so when I'm here, some of these capacitors, if I've properly designed this here, some of them are can be viewed as short-circuited for the most part, and some of them can be viewed as up until that point as pretty open circuit, right? Because you're getting flat response there. So which ones are, in this example, which one is the short-circuited at this point? It can be viewed short-circuit. CC, right? If you have to properly design, if you have properly designed it, you don't want this to be blocking anything, right? You, in a band of interest, you want this to send everything through. And which one is open circuited? C pi, because it hasn't started kicking in yet. The frequency is not high enough for it to matter. So now if you notice, you can actually break this circuit into two equivalent circuits, right? You can say that for the very low frequency part of the behavior, this is your circuit. And for the high frequency part of it, this is your circuit. Right? So you can do this decomposition on a circuit itself without having to do it in mathematics necessarily. I mean, you are doing it mathematically, but so that's the decomposition. So if I look purely at this circuit, what kind of transfer function would I see? Do you agree that you will see, for the red circuit, this is the transfer function? Right? And for the blue circuit, this is the transfer function. So now you have to kind of be judicious about this, meaning saying that if you want to so you can still use the method of zero value time constant for estimating omega h, but to do that you have to really you have already short-circuited all of these capacitors that are intended to produce the bandpass response in this case, right? So this is the circuit you will go and analyze. And if you analyze this, the time constant, this which is going to be still this time constant, would determine your bandwidth. In this case, since it's a single time constant circuit, your omega h is exactly 1 over tau pi 0, because it's a single frequency, single bandwidth, single energy storage element for that circuit, right? Any questions on this? But you can see if I blindly apply it, then I will get something that has nothing to do with this bandwidth. It's something else. And this is probably the simplest example that you can make. Generally, there's a bunch of capacitors that fall in this category and a bunch of them that fall in this category. So if you want to analyze, if you want to look at this part of the response, you get all of these coupling capacitors and bypass capacitors and all those things, and you short circuit them. There could be chokes, RF chokes, inductors, things of that sort. You open circuit them. And then you analyze what's left, which is a lot easier because it has fewer capacitors or inductors. We'll see more examples. So we will, when we develop the IVT, the infinite value time constant, we'll see a more systematic, broad way of kind of analyzing this part of the transfer function. But this is just to give you a preview of how, if you just, ZVT can by itself fail. Or not give you exactly what you expect. It will give you what it's supposed to give you, which is B1. But B1 may not be what you expect. Yes?
Is Emit like approximately the gain when CC is shorter than C5 is open?
Exactly. Emit is, that's a good question. Emit is exactly the gain that when CC is shorter than C5 is open. Which in this case would be the resistive divider at the input, which is R pi over R1 plus R pi times negative GM R2. So that would be your gain. The gain from here to there, and then from here to there. Right? The gain from here to there, if this was shorter and this was open, right? The gain from, you have an R pi here, so you have a resistive divider. So it's R pi divided by R1 plus R pi to here, and from here to the output is negative GM R2. Or R2 over Rm. Negative R2 over Rm. Okay. Any questions on that? All right, good. So now let's get to a third example that leads us to the first modification to this, this first improvement. That a lot of times may not be necessary, but the key is to know when it's necessary. The approximation is an art, and the key to it is understanding when you need to approximate at what level. It's the key. You want to use the simplest model, especially if you're designing, right? The simplest model that gives you the essence of what you're trying to design. You don't want to make it any more complicated than that. But to do that, you have to understand different levels of sophistication, and you say, okay, now this is a scenario where I can use this ZVT, and 80% of the times I can use the ZVT as is, and that's not a problem. Out of those remaining 20%, right, there are modifications and changes that you need to think about and you need to be aware of to make them more advanced approximation. Or sometimes you just say, okay, I'll need to go to the exact because there's some nuanced thing that's happening or verify something. Okay, so let's look at another example. So the next example is essentially one of our previous examples with one modification. So here's the, let's see. Yeah, let's keep it here. That's fine. So this is essentially the first circuit we started in our design example last lecture. So it's basically the common emitter. And we'll make one modification to it. So this is R1, R2, Vn, right? And then you have a CL. We have a C mu, you have a C pi. So this is exactly what we had, the first pass of our design, right? And this is V out. V out, the values of the components were C L was 200 femtofarads, if I'm not mistaken. C pi was, what were the values? 100 femtofarads. 100 femtofarads, and C mu was 20 femtofarads, the same values. And then we also had and GM was 40 millisiemens. What else did we have? R1 was 1 kilo ohm, R2 was 2 kilo ohms, if I'm not mistaken. I think those were the numbers. Yeah, okay. So this is exactly the same circuit. You remember when we did this, the bandwidth I think we estimated was 95 gigahertz, and the bandwidth we simulated was 97 megahertz. Something like that. Yes?
Is the resistor on the base supposed to be R1?
Yes, yes, thank you. R1 and R2. Yes, thank you. Yes, but so we estimated for these values, we estimated, Sims gave you FH of 97 gigahertz, and ZVTs gave you FH estimate of 95 gigahertz. Okay? So this was the first pass of our design. Now we are going to make one modification to this. We're going to add one extra capacitor. I'm going to add an extra capacitor here, C1. And C1, I'm just going to throw something at you, and we'll see how I got this, is 4.3 picofarads. It's a pretty big capacitor, relatively speaking. I'm just going to throw that at you. Okay? I just added one extra capacitor there. So what do you think this is going to do? Well, first of all, again, how many poles, how many zeros? 3 poles now, right? Do we have 3 poles, really? Let's think about it. To determine the poles, how many poles you have to first null the independent sources. And if you null the independent sources as far as the time poles are concerned, how many initial conditions can you tell? Can you make? 2 still, right? Because see, if I null this, when I null this, these 2 capacitors are in parallel. So I still have that capacitive loop, so I have only 2 poles. How many zeros? 2 zeros, exactly, right? Because there's a maximum number of elements that I can simultaneously infinite value is 2 now, because I can simultaneously infinite value these 2, and the input will directly be connected to the output. So it's basically just non-zero transfer function. So I have 2 poles and 2 zeros. Now, this is the interesting thing. As far as the pole evaluation is concerned, these 2 are in parallel. But as far as zeros are concerned, they are not. Because now for zeros, you have to look at transfer constants. So you have to be careful about them, not blindly putting them in parallel. Okay, now let's do our thing. I mean, we did the time constants before, right? What were the time constants? So there was a tau pi 0, which was the resistance seen by this guy, which is R1 parallel R pi times C pi, right? There was a tau mu 0, which was the R left, which is R1 parallel R pi plus, so it's C mu times that. C mu times R1 parallel R pi plus R right, which is R2 plus GM R2 R1 parallel R pi, right? And then there was a tau L 0. We did this last time, so I'm going to do it quickly. CL R2. And the values we calculated for these, if I'm not mistaken, if this was like 70 picoseconds, right? This one was, I think, 1200 picoseconds, and this one was 400 picoseconds. I think it was 1200 something. Or 1200. Okay. Now, we have one more time constant, right? Due to this new capacitor. So let's call it tau, 1, 0. So what is that? It's C1 times the resistance seen by C1 when all the independent sources are nulled, which is what? So as far as that guy is concerned, from his pole perspective, it looks the same as C pi. So it's basically sees R1 parallel R pi, right? So it sees R1 parallel R pi. So that's like, and if you calculate that, it's like something like 3,000, I think, 3,770 or something like that. 3,070 picoseconds, yes. Okay. So now let's look at this and see what it does, what happens. Okay. What's the new time constant? What's the new sum of the new bandwidth estimate, right? If you calculate these things, add these up, so you get a sum of the time constant, which is now going to be larger. And if you approximate your omega h with that, you will get, from that estimate, you get about 2 pi times 34 megahertz, which is expected, right? Because we were at 97, 95 megahertz before. Now you have a time constant that's even larger than that. So you add it up. So you had the total time constant was 1600. Now you've added almost twice as much. So we went to 34 megahertz bandwidth estimate, right? So now, then we'll go and do a SPICE analysis. Okay, so that's on page 163. Let's see what it shows us. So what do we see? What does that look like? First of all, the bandwidth, the simulated omega h. So now omega h simulated, so this predicts this, but then the simulations predicts a bandwidth of 482 megahertz. More than a factor of 10 higher. So now this is 10 times higher than what you estimated the bandwidth to be. It's still, your estimate is still conservative, but it's way off. Right? So what has happened? Look at that transfer function. Look at the Bode plot that we have, and see what you see. So the amplitude plot, you will see that it goes from the slope, it's flat, then it starts dropping, right? And the slope is negative 20 dB per decade. It corresponds to a single pole. And then it becomes flat again, which means that a zero has kicked in. Now, is this zero that has kicked in left half plane or right half plane? You can look at the phase response, and you see the phase hasn't come back up. It actually is added. So it's a right half plane zero, right? So you can see that too. So from what you see a single pole and a single right half plane zero. So what has happened? So what happened? What do you think? Do you have a hypothesis about what's going on? Yes?
As the frequency increases, C1 starts getting shorted, so the resistive divider between R1 and Rm starts going away.
Yeah, good point, right? He says as the frequency goes up, C1 starts getting shorter. So you see, remember, part of your gain is coming from this frequency resistive divider, right? Yeah. So as this guy starts fizzling out, right? Because of these capacitors, the gain starts dropping of this part of the circuit. This guy says, okay, you know what? I'm going to increase your input. That's one way to think about it. Because now the resistive divider ratio gets larger and better and larger because this resistor becomes smaller than that resistor, right? That's one way to think about it. This part starts dropping, and this part starts picking up. So in the beginning, they start canceling each other. Of course, at some point, some other things will kick in. And this cannot do it forever, right? That's good intuition. That's good way of thinking about it. We can also say it in many different languages. We can say it in the language of poles and zeros and what's happening. So can we say it in the language of poles and zeros? The introduction of that capacitor introduced what? Another zero. Now you saw that I picked some sort of an arbitrary looking value for C1, right? It looked 4.3 picofarad. We'll calculate that in a few minutes. We'll see how we arrive at that in a short while. How you pick it. Now if I had picked it to be any other value, like say if I had picked it to be like 7.5 picofarad, this would not have happened. I mean, the gain would have not been as high. I picked the right value, really. But what happened is that you introduced another zero. So what did I do with that zero? You remember, this circuit without this guy had two poles and a right half plane zero that was at pretty high frequency. Okay? But, so it had two poles. It had one dominant pole, if you remember. The dominant pole was at the input, which is this basically this resistance with this Miller capacitance, Miller equivalent capacitance at the input. Right? That gave you a capacitance there in parallel with R1 parallel with R pi. That gave me a first pole. So how do you think I chose the value of C1? Where did I put my 0?
Cancel out that dominant.
Yes. So we picked that value of C1 to be sitting dead on top of that first pole, to the extent that you can. So that capacitor came in, that 0 came and sat right on top of that first dominant pole. So now what you're hit with is your second pole. So what you see in that Bode plot, that first drop, is that second pole, because your first pole you've already killed. And then what you see when it flattens out is that right half plane, very high frequency 0, due to this guy, which was flipping the polarity. Does it make sense? What's happening there? Okay, so how do we choose that? How do we pick that value? We'll see in a second. We'll see in a second. But let me do another example, and then that will lead us to the modification need. So you can see that as a bandwidth estimation, we have failed. ZVT has failed here, really. I mean, I would consider this a failure, right? If you're more than an order of magnitude off, you failed. So, okay, so let's talk about a simple example. So let me just move this here. And open up some space, and then go here. So let's make a simpler example. This is something that you probably have seen. We talked about it in 44. You may not remember it, or you may have seen it somewhere else. It's a simple circuit. Imagine this circuit. It's purely passive, in fact. V in R1, R2, and C2. So what kind of a bandwidth, what kind of transfer function is this? This is a low pass, right? Because as the frequency increases, this starts shorting it, so you will get a response that it's a first order low pass, right? And what is the cutoff frequency? You can tell it from time constant of C2, right? You can calculate the time constant for C2. It's basically tau 20, which is the resistance seen by this guy when this is null, which is R1 parallel R2, C2, right? So that's the time constant for that guy. Now, and what is the H0 for this guy? When you set it to 0, basically you have a resistive divider, right? It's R1 over R2. This happens in a lot of situations, right? You have a capacity, something that you're driving with the source. So this is basically the situation these kind of things happen. You have a source with a source resistance that drives a load that's supposed to be resistive, but it has some parasitic capacitance. And that's why you get the low pass response. This happens a lot. So this is the transfer function, and this what it is. So it's a low pass response. And if I ask you what is H2, not that it particularly matters in this case, H2 is what? How do you determine H2? You set elements with the index 2, which is this C2 now, to infinite value, meaning short circuited if it's a capacitor. So what is H2? What's the transfer function or transfer? 0. So this transfer constant is 0. All right. And if you know these two, you can calculate, basically you can write the H of S, right? The H of S is simply, so you have no zeros and you have one pole. You could tell without even writing any of this stuff. And it's basically 1 plus R1 plus R1 parallel R1 parallel R2 C2S. This is the transfer function of this thing. It's a basic first order low pass. Now, if you introduce a second capacitor here, the capacitor C1.
What happened to the H0?
Oh, you're actually right. I'm sorry. Yes, this is H0 times that. Thank you. I should have, what I meant to write, which I didn't, was this. Yes, you're right. Thank you. Okay, so now if I introduce that new capacitor, what changes? That added capacitor. First of all, what's the order of the circuit with this new capacitor? How many poles, how many zeros? We had one pole and no zero before, right? So look at it and tell me how many poles and how many zeros. How many poles? One pole, right? Not two. Why one? Because if you short circuit this thing, you have a capacitive loop. In fact, you have these two capacitors. In this case, a special case of a capacitive loop. The case of capacitive loop with two capacitors is called two capacitors in parallel, which is also two capacitors in series. But yeah, but the two capacitors in parallel, really. But if there are other elements are involved, then it would be two capacitors in parallel, not two capacitors in series. But anyway, so there's one pole. How many zeros? 1, 0, because you can short circuit this and then you get some. And it's a left half or right half plane 0? It's a left half plane. And my pole is left half plane. So that gives you some sense that maybe if I have a left half plane 0 and a left half plane pole, maybe I can put them on top of each other and get them to cancel each other. So let's see if we can. So what is it? Well, to calculate that, first of all, the first thing you need to calculate is H1, right? So what is H1? What is H1? When you infinite value C1, what's the transfer function? 1. You're shorting the input to the output, right? So it's 1. And, OK, so what is the new transfer function? The new transfer function is, so if that's and H2 is still 0, so I know A1 is simply the only term in A1 that's non-zero is tau 1 H1 0, and we have to calculate tau 1 0. What is tau 1 0? What? Parallel R2, right? Again, R1 parallel R2 C1, right? So now A1 is this thing, which is basically now H1 is 1, so it's simply basically R1 parallel R2 C1. And B1, which is the sum of the two time constants, sum of the two zero-value time constants, is basically the parallel combination of the two resistors times the sum of the two capacitors, which is also their parallel combination. Right? So those are the B1. So we know our transfer function because that's it, right? Because it has one pole and 1 0. So our transfer function, if I ask you what's the transfer function, you can write it. Now, what we can do when we write that transfer function, if I factor H0, you will see that H0 has an R2 over R1 plus R2, and A1 has an R1 R2 over R1 plus R2, right? So if you factor that part, that R2 over R1 plus R2 part of it, then what's left is going to be simply R1 C1S. And the denominator is going to be 1 plus R1 parallel R2 C1 plus C2S. So that's the transfer function, if you want to write it in terms of the parameters of the circuit. Now, what are we trying to do? We are trying to set the frequency of the pole and the zero to be equal. Let's see if we can do that. Basically, it means that R1 C1 should be equal to this thing. Let's see if that's possible, because that may not be possible. Let's write it. So we can say R1 C1 equals, and we will expand that parallel combination, R1 plus R2 times C1 plus C2. So this R1 cancels that R1. If I multiply this both sides by R1 plus R2, I get R1 C1 plus R2 C1 equals, and on this side I get R2 C1 plus R2 C2. These guys cancel, so the condition for that to hold is this. It's not worth really boxing. It's just maybe just underlined. Okay? So if the product of R1 C1 and R2 C2 are equal, then your pole and zero cancel. And you will get a flat response up to infinity, actually, if this is all of your circuit. So basically, your response becomes flat. It's like a wire. So this can be used in several different ways. This is used a lot. Most likely you've used it already in the lab. If you've used an oscilloscope, you've used this. The oscilloscope probes, you've noticed that there's a 1x and 10x on them, right? Almost all of them. Why is there a 10x? Why do you want to have a 10x on an oscilloscope probe? Basically what it does, what it is that the input of the oscilloscope looks like this, right? So you can try to connect it directly to your whatever your source or whatever it is that you're trying to measure, and then you will get a low-pass response. Or you could introduce an extra resistor. In this case, in the case of a 10x, they make it 1 to 9. So it's 10x attenuation. But then you add an extra capacitor. You're adding an extra capacitor. And you're making it balanced out. And this is another example where it's not just if you're adding more capacitor, the circuit's bandwidth is going to go down. There are lots of cases where we add. I mean, the example we had last time, right? We started with 1 transistor, and we ended up with 3, which has clearly more capacitances, but their bandwidth significantly improved. It's not just the number value of capacitor. It's where they are connected and what they are doing. Same thing with inductors. So they can actually help or hurt. Now, intuitively, what's happening? Why is it that if you pick these values right, this doesn't drop, the gain doesn't drop intuitively?
The capacitors kind of go out of phase to cancel each other out.
Kind of, yeah. I mean, there's one way to think about it. That, yeah, kind of. You could say they're going out of phase. But what it is think about this as an impedance, Z1, and this as an impedance, Z2. If I choose Z1 and Z2 so that they scale the same way with frequency, if they both drop with frequency at the same rate, the ratio which will determine the division, I guess the voltage division ratio, right, is Z2 over Z1 plus Z2. If Z1 and Z2 drop at the same rate, then that ratio is not going to be affected. That's what's happening. Does it make sense? So they both become smaller with frequency at the same rate, and that's basically drop. Now, this is used in oscilloscope probes and all that. So let's go back to this circuit and see what we did. And how did we pick this value? How did I pick this 4.3 picoseconds? Do you see a similarity between these two? So this part is just this part, right? So what I could have done, or should have done, or I did, is basically said, okay, what does this input look like in terms of an RC? What is the equivalent of RC? The R part of it is simple, right? What is the R part of it? What is the equivalent of R2 here? R pi, right? What is the equivalent of C2 here? It's the total equivalent capacitance I see at the input. You remember we had the Miller multiplication, right? Input Miller capacitance at the input. What was it? Do you remember what it was? It was C pi so C total at the input is C pi plus C mu times 1 plus GM R2, right? The Miller multiplication factor. If you calculate this capacitance, what is the CT of this capacitance? So the Miller capacitance is 1.725. So this is 1.72 picofarads. And we can calculate. Like this is 80, right? This was 1. So it's 81 times 20 femto, sorry. So it's 80 times 20, so it's like 160, 1.6 picofarad. And then there's another 100 femtofarad, so that becomes 1.72, right? 1.72 picofarads. So that's CT. So that's essentially my C2 here. So what I'm trying to calculate, what I'm trying to enforce is that I'm going to say C1 is going to be CT times R pi divided by R1, because I'm trying to enforce this relationship. Right? And if you do that calculation, so you get CT times R pi, which is 2.5 kilo ohms, divided by 1 kilo ohm, and that would be 4.3 picofarads. So that's how I chose that value. And that's why the intuition that Richard mentioned earlier, right? So that as the gain of this guy starts dropping because of this dominant capacitance, this is picking up, which is the same intuition kind of here. They're the same thing. Okay? So now the key question is, how do we take this into account in our analysis? Can we come up with a modification to our method to take this into account so it doesn't give such a drastic error? And we'll do that after the break.